Attendees should verify that this material meets the requirements by the PE board in your particular state, since some state requirements differ. Thank you for joining us, and I'll hand it over to Serge.
Thank you, Jocelyn. Good morning, everyone. Thank you for joining us on this second part of 3 series on the control valve sizing theory, the exciting world of control valves. That's the fun part of what we do. So let's talk a little bit more about the theory on cavitation, flashing, and everything related to the potential downfalls of on using the wrong valve in the wrong place, and try to help everyone pick the right valve in the right place to do the job it's intending. There are no bad control valves, they're just applications or misapplications. So we're going to try to help demystify all this, give you rules of thumb as we go along, and we hope to have as many questions that we had last time. We were overwhelmed, and unfortunately some of you put their name as didn't put their name, so we can't answer all of you specifically. We wish we could. So please send your questions, and I will try to answer them as we go along as well. And look forward to a good series. So first, we're going to talk about the valve pressure recovery factor. It's one of those factors that show up on manufacturers' specification sheets or technical documents, and it's one of the most important part in the control valve sizing formula. Why? Because the pressure recovery factor will determine or says how much pressure drop a control valve can take before the liquid fluid going through it would cavitate, and that number is very important. And it is a number that's determined by testing, and it's also dependent on the geometry of the specific control valve. So what's the pressure recovery? Is the fluid passes through the valve orifice, and then there's a marked increase in velocity when you're going through an orifice, because the fluid going through a pipe will have to accelerate when it goes through an orifice, and the orifice in this case is a control valve. And when the velocity reaches a maximum and pressure drop is at a minimum, or the smallest sectional area just downstream the orifice, this point in maximum velocity is called the Vena Contracta. So it's the highest velocity is not where the control valve is actually throttling the flow, it's just past that. So depending what type of valves we're looking at, that Vena Contracta may be inside the valve body, the theoretical area, or it could be outside of the body. So depending how long the face-to-face of that control valve is and the internal geometry. The more streamlined the body, just like a butterfly valve or a ball valve, you have a high degree of pressure recovery. The reason is the throttling area is between the disc and the seat in the butterfly, or the ball and the seat in a ball valve. Where in a globe valve, what you get is the body of the valve itself is much longer, and it has a more tortuous pass through the body. And that tortuous pass create a pressure drop across the whole length of the body, not necessarily between the plug and the seat in a globe valve. And so the pressure recovery factor is used to quantify the maximum velocity at the Vena Contracta, and is derived by testing, and it's published. So it's a number that you can get from the manufacturer, and the higher that number is, the more pressure drop that valve can take before it cavitates. So we'll look at that through the presentation, and the recovery factor is called FL in the formula for valve sizing. And now I'll pass this on to Ralph to continue.
So as Serge was describing what the FL recovery factor is, there's a depiction of fluid flow through a restriction. So P1 is your upstream pressure, and P2 is your downstream pressure. And in order for the fluid to pass through the smaller area, which is usually the valve trim, the velocity increases And because of conservation of energy and a principle that was named after a gentleman called Bernoulli, Bernoulli's principle, if you have an increase in velocity, you get a counter drop in pressure at that point, and then it recovers downstream. So the curves are shown on the bottom below. So your velocity will spike, and then as your velocity goes up, your pressure will drop at that particular point, and then it will recover downstream as the area of the pipe increases, and then you also get the velocity decreasing and going into the bigger area of the downstream pipe. So valves are low recovery valves, or are valves where that spike doesn't make as big a dip. And high recovery valves, the velocity is very high through the Vena Contracta, and the pressure profile, the pressure drops significantly through that point. So one of the key elements of doing sizing for liquids is knowing the vapor pressure of the liquid. And this is the pressure at which point the liquid changes state and changes into a gas. So essentially, if you drop a liquid below this vapor pressure, you will basically change it into a gas. The other term we've been discussing is the pressure. We talked about the Vena Contracta, where that pressure drop occurs when the velocity is the highest. And we have a term for that. It's P sub VC. So the vapor pressure is PV, and the pressure of the Vena Contracta is P sub VC. And the differential pressure we'll be discussing. Differential pressure, basically, to define that again, is the upstream pressure less the downstream pressure. And you have to have a differential pressure in order to have flow through the valve. So P1, if P1 is equal to P2, you have no flow going through the valve. So there always has to be a pressure drop. And that goes for piping systems and everything else. You have to have a pressure drop to move fluid downstream. So this is the basic formula to determine the valve recovery factor, F sub L. So on top is the P1 minus P2, which we just defined as the differential pressure. And the bottom of that fraction is the upstream pressure, P1, minus the pressure at the Vena Contracta, which is done by testing of each valve geometry. So this is the profile of the flow through a valve seat where it's throttling. So you end up with, you have an upstream pressure, you have a spike in velocity, which will then drop your pressure going through that orifice, and then it recovers downstream as the area of the pipe is larger. And you do lose some pressure due to turbulence. So that ends up being your differential pressure. So the more turbulence you introduce into the flow, the more of a differential pressure you end up with downstream. You have a lower pressure downstream. So this is just a comparison of the different profiles based on what the recovery factor is for different geometries of valves. So you see globe valves are called a low recovery valve because they don't have as deep a spike in pressure when they're throttling. Whereas more, if you go down further down, the butterfly and ball valves have a deeper spike because they're more streamlined and they allow more velocity through. Now this F sub L factor does change with the percent open. So most manufacturers will give you a CV table, which we'll talk about later, which is the capacity table, and below that there'll be a line that will have the F sub L factor for each percent open. So the recovery factor depends on the percent open of the valve. Because the wider open the valve is, the faster the velocity can accelerate, and the more the valve is throttled down, then the less the velocity it'll give it more of a tortuous path, depending on the valve geometry.
So Ralph, when we look at this and you look at a globe valve, in this case, it's got a low recovery, so which means that it can take more pressure drop through the body before it starts to cavitate versus, let's say, a ball valve right here. So when somebody looks at that, they may think, well, the globe valve is the best valve for control, right? And they would be correct if the job of that control valve is to drop a lot of pressure. But I think that it's important to look at this in another way, is that if the job of that valve is to control a fluid and have the least amount of pressure drop through it, then a ball or a butterfly will do a better job than a globe valve would do. In fact, if you do a calculation, I've done it in the past where customers said, I want a globe valve for control, and then you do the calculation, the globe valve cavitates, we ended up putting a butterfly valve in that calculation, and because of the high flow potential of the butterfly, did not create any cavitation at the same flow rate. So every valve's got a job that can do, and it's got its limitation. And globes are good for delta P, and ball and butterflies are good for flow and very or low pressure drop control.
Yeah, globe valves, the fluid has to make 2 turns to go through the trim. It's usually down either under or over the plug and then out. So there's usually 2 turns involved in the flow path through. Rotary valves, there can be 2 turns, and that's why when the valves are closer to being closed, they have a higher recovery factor because the fluid has to turn to get out of the valve. Whereas when they get further open, then there's more of a streamlined shot for the fluid downstream, and that's where they get the higher velocity potential.
Got it.
So this is an application of a good valve. It's got your upstream pressure, which is the P1, goes through the trim of the valve, and you get your high velocity spike, which is the yellow line, and you get your counter pressure drop at that point, and then you recover downstream, and there's no issues with this valve. The pressure drop at the Vena Contracta is not violating the vapor pressure of the fluid. So this is just a perfect application in a liquid service. This, on the other hand, this chart shows that your P1 pressure accelerates and the velocity increases to the point where it drives the pressure at the Vena Contracta below the vapor pressure. So what happens? You get a phase change. You go from liquid phase to gas phase. A percentage of the liquid will form gas bubbles because it's now being told it should be a gas at that pressure. And then what happens downstream is the pressure recovers because of the larger diameter, and you get the bubbles collapsing. So you go back to all liquid phase at that point.
So that area is where cavitation occurs after it goes back through the vapor pressure down here. So you start to get cavitation beyond that point. So that may be inside the control valve or outside of the control valve, depending what the geometry of the valve is. But at this point,
and the velocity.
Right. And at this point here, this is just vapor bubbles being created.
Right.
So that's not a problem yet. The problem is really here.
The problem is in the recovery.
Right.
So we'll show that in the next slide. So
you may have problems here due to the capacity of the valve, because obviously if you're creating vapor bubbles, you're removing some area for the liquid to go through. So it would start choking the flow a little bit because of the gas is going through the trim.
Right. And then you would gas is much higher volume than liquid, so it would eat up the area in the trim really quickly because the volume of the gas is so much more than when it was in liquid form.
Right, and because you're creating these bubbles, there's less room for liquid, so that means the liquid needs to accelerate even further to be able to go through the same orifice, so that velocity increases a lot faster at that point.
Yep.
So you're really trying to find a valve that's not going to go through vapor pressure. That's the whole point of calculating the CV and also calculating the potential for cavitation.
Yes, I think the next slide will explain a little better. So what happens is this gas bubble forms at that point in the Vena contractor where you violated the vapor pressure of the fluid. And depending on the fluid, it will determine how much energy will be stored and then released in these vapor bubbles. So the surface tension of the fluid will dictate that. So water, ammonia, there's a whole series of liquids that have a very high surface tension. And surface tension basically is the resistance of the surface to be broken or penetrated. So on water, you start out with a gas bubble forming, and then because of the surface tension, when it goes downstream and the pressure recovers above the vapor pressure, it doesn't easily collapse immediately. It compresses, and it could compress up to hundreds of times more than the pressure inside could compress the gas to hundreds of times more than the line pressure. So now you have a bubble that was a big gas bubble. Now it got compressed into a little gas bubble with a lot of pressure inside of it. And when it finally, the surface tension gives, it releases a large amount of energy. And if that energy is released against a metal surface, it will fatigue the metal surface and start to wear away or chip away at the structure of the metal. So people say that cavitation sounds like rocks in the pipe, and the rocks are highly compressed gas bubbles. So when these bubbles compress, there's high pressure gas inside, and they're very hard, and that's why they sound like rocks. And then when they finally do compress and release, if they compress and implode in the center of the fluid flow, there is no damage. So it's only when they compress and release their energy against the metal surface that damage is caused. So the damage is very rough because it's a pitting, it's a fatiguing of the metal and basically chipping away at the metal with jets of gas that are released. So you can see the plug in the seat on the right, and then there's a rotary valve. You get the same kind of damage in a rotary valve as well, and just depends on how big of a pressure drop you're taking as to where that damage will occur, where the valve bubbles will implode. If you take the higher the pressure drop, the further downstream your bubbles will implode, obviously, because the velocity will be a lot higher.
So when you're looking at damage like this, where it looks like something's been eating at it or basically pulling metal pieces off of a trim or a valve body, that's cavitation.
Right, it's very rough. So there's two different kinds so at full cavitation, the cavitation bubbles consume the trim outlet area of the valve until the flow is choked, so you can't pass any more flow. But you also get, it's a gradual phenomenon. So you'll violate the vapor pressure a little bit, and then as your pressure drop increases, your velocity will increase to where you'll build up to where you're at full cavitation. So it doesn't just all happen all at once. There's a little starting point, and then there's gradually, well, not gradually, but depending on the pressure drop, it'll move up pretty rapidly up to full cavitation if the pressure drop continues to increase.
I guess it's like when you're boiling water, you got a little bit of bubbles at first, and then you have a lot of bubbles when you heat up more. But in a valve, we're not heating the liquid, we're reducing the pressure, which does the exact same thing. So as you boil more water because you reduce the pressure, you have more gas. And then the full cavitation, the way I understand it, is that point where all of the liquid or enough liquid have been turned into gas where the velocity in the pipe is at the speed of sound. And at that point, you can't go any faster. You can't create any more bubbles. That's what it's called choke flow. You can't have more flow because there's no room for it.
Right. That's why they use vacuum fractionation towers in refineries in order to vaporize the gases in the crude oil.
Right, without having to heat it as
Without
much.
having to heat it, exactly. So you just drop the pressure.
Yeah.
So flashing, so what's flashing then? So flashing occurs in the same way that cavitation occurs. You have a high velocity spike at the Vena contractor, you get your counter pressure drop at that point going below the vapor pressure. The only difference here is that the downstream pressure is below the vapor pressure. So the outlet of the valve is below the vapor pressure. So the bubbles don't have any recovery pressure to collapse. They just stay in the gas phase. So this causes a very high velocity, because you now have a lot of gas being formed and its volume is many times more than the liquid, and it's trying to fight with the liquid for the space inside the pipe. So the result is an acceleration of the velocity of the liquid downstream. So you get a very high velocity of gas and liquid downstream. And now you have two-phase flow. So the outlet of a valve in flashing service downstream is two-phase flow, gas and liquid.
So when you're transforming the liquid into a gas, obviously it's going a lot faster to pass the same amount of mass through the pipe, right?
Yep.
So if that's the application and you have no choice, you're going from P1 to P2 and you're going to remain in gas, do you need to do anything on the pipe outlet as far as the size is concerned to create less velocity?
Yes, well, and when we go to remedies, you do, when you have gas in your fluid, you need to expand the outlet diameter of the pipe in order to accommodate the increased volume of gas that's being created by basically flashing the liquid to gas. This is used in some processes on purpose. Sometimes it's unintentional, but because of the temperature of the fluid, you end up making two-phase flow. In some places, they actually want to make two-phase flow. They want to flash the gas into liquid, I mean the liquid into gas. But what you end up with is damage that's really smooth to the valve trim, because you have very high velocity fluids going across the metal, and it wears it at a high rate. And the more, if the fluid is corrosive, the velocity increases corrosion exponentially. So if you have any kind of issue with corrosion, it'll corrode the metal that much quicker, exponentially quicker. So the damage is usually smooth. So you get very smooth damage because you're eroding and basically you're wearing away the metal with the velocity. So let's compare cavitation to flashing. In cavitation, you can address cavitation by selecting a lower recovery valve, or changing the valve size to where your valve is not as far open. So that will sometimes help, because then the F sub L factor for a valve that's 20% open will be higher than the valve is 40% open on a rotary valve typically. Or you can go to a globe style valve. If you can't address that by doing those things, then you can go to a what's called an anti-cavitation trim, which basically limits the velocity through the trim. And that the limiting factors typically are using drill holes or turns to slow the velocity through the trim. So if you slow the velocity through the trim, then you don't get as big a spike down in the pressure at the Vena contractor. So that's the purpose of the drill hole cages or multi-turn trims. That's limiting the velocity of the fluid going through the trim. And then if you want to use a more economical, say you have a very big valve, you have a 10-inch valve, and an anti-cavitation trim solution will be prohibitively expensive, then you can always put a plate downstream with drill holes in it, and basically that creates a stage of pressure drop that will slow down the velocity through the trim of the valve because it puts an additional back pressure on the valve, so the valve won't take as big a pressure drop because the plate will then take part of the pressure drop. Flashing you can't address, you can't eliminate it with valve trim or valve selection because it's a process phenomenon. You have the downstream pressure is below the vapor pressure, and so unless the process can be changed, there's no way to mechanically eliminate it. But what you can do is basically armor plate the trim of the valve. You basically overlay the valve and make it with some kind of stellite or other hard material to withstand the velocity, erosion or corrosion. Carbon steel, if you're flashing water, carbon steel is a very bad choice for a valve body because basically the gas in the water will rust if you want to call it that, it'll rust the carbon steel body and wipe the rust away quickly. So the bare metal is constantly being exposed to the velocity of the corroding gas that's in the bubble. So you'll get a lot faster wear of a carbon steel body in flashing service. So that's why we recommend going to an alloy body in order to avoid that scenario if you're flashing water.
Also on the cavitation side, you can add multiple valves in series so that you can drop the pressure through both or 2 or 3 valves so that the Vena Contracta is not so high. The velocity
so
is not
give
so
you
high.
two, yeah, you'd give you an adjustable, instead of having a fixed orifice plate, you'd have an adjustable, two adjustable orifices.
2 adjustable orifice plate.
Right.
And sometimes it's cheaper than one multi-plug globe valve to do the same job. While
yes, it's all driven by valve size. Like I said,
Right.
in the smaller sizes, 2-inch to 3-inch valves, the severe cavitation controlling trim are a lot less expensive than when you get up to 8-inch, 10-inch, 12-inch valves, and you have prohibitively expensive valves. So some of the remedies we were discussing for cavitation is an anti-cavitation trim or trims that direct. So as was explained earlier, if your cavitation bubbles implode in the middle of the fluid flow, then there is no damage because they're releasing their energy in the liquid and they're not affecting any of the metal surfaces. It's only when the bubbles implode against the metal surface that you get damage. So some anti-cavitation trims redirect the cavitation bubbles to the center of the flow, and that's how they control. So they don't eliminate the cavitation. They're basically cavitation control trim. It's controlling the damage potential. And basically, the other way is to try to eliminate it. You try to minimize the velocity by not taking the full pressure drop through one orifice. You make it go through a couple of different orifices or turns in order to slow down the velocity at the Vena Contracta and then eliminate the spike in pressure below the vapor pressure.
These are interesting trims on the right here. So those I think are metal printed flow patterns through V-ported ball valves, which then create a multiple pressure drop area. Is that what you're talking about?
Right. That gives a second stage to the pressure to minimize the velocity spike all at once.
Right. And with metal printing, there's so many possibilities now. They're almost infinite. It gives the valve designer a lot of room to create all sorts of different flow patterns.
And then when you get into larger valves, you can actually put a downstream plate as part of the valve body or valve body system. So you can sell a whole package with a plate built into the valve body. as a solution. So it's basically doing this, accomplishing the same thing. You're taking the pressure and slowing down the velocity in order to minimize the spike at the Vena contractor. So you drop it twice.
So you have a variable orifice plate here behind the ball, their segment, and then you have another fixed one here.
Right. And then this scenario, you use a back pressure plate. Now the disadvantage of putting a plate downstream is it limits your rangeability, because now you have a fixed orifice downstream, and you can't vary that CV. And then you also have an issue with the valve now may have to be a larger size. So if you were taking, when we get to the CV calculations, you'll see what this makes a difference. But the valve may have to go up a size if you put a plate downstream, because now the pressure drop through the valve is not as high as it was, and it's lower pressure drop through the valve, the higher the CV. So required. So the two disadvantages of using a plate is, one, makes the valve bigger, and two, you limit some of your adjustability of your flow, because you have a fixed restriction in the pipe. So choke flow, we were discussing earlier. The choke flow term means that the gas phase of the liquid has consumed the volume in the trim to where you can't get any more flow through the valve. So that'll occur with flashing or cavitation. Either way, when you change phase from gas to liquid, the gas is much higher volume and will consume the area in the throat of the valve that you want to pass fluid through. So graphically on the next slide we'll show. So it's all determined by the recovery factor of the valve, or at what point your flow is choked. So the higher the differential pressure, the more flow you can get through the valve. So, but you'll reach a point where you can't, because you'll hit a point of where you're forming and violating the vapor pressure of the fluid. You'll have so much gas volume in the valve trim that you won't be able to pass any more flow, even if you increase the differential pressure by lowering the downstream pressure. You won't get any more flow. Now, if you increase the upstream pressure, you can get more flow, but you'll hit another point where the gas will increase enough to where it will choke the flow, and then you'll stop passing any more fluid.
Is it at this point, Ralph?
Yep.
Okay.
So you're choked at that point.
Yeah.
So there's a formula for that to determine that. So it's, if your differential pressure is greater than that, you're okay. But if the equation on the right is greater than your differential pressure, you're at choked flow. So there's so the components of that formula is your F sub L squared. So this is the F sub L is an ISA term that now everybody has pretty much accepted and translated their formulas into. For a period of time, every valve control valve company, a lot of them had their own formulations with their own signifiers of what the recovery factor was. Mason-Nealon used to call it C sub F, and Fisher used K sub M, which just recently they've converted to the ISA standard of F sub L. But the Fisher K sub M, basically what it was is this F sub L squared. So the K sub M in the Fisher formula is the F sub L squared. So they already, since it's being used as a squared number in the formula, they just squared it in advance. So that's why if you're doing a comparison of their formula, they already squared, their K sub M is equal to F sub L squared, approximately. And then what we have, the rest of the formula is your upstream pressure minus your vapor critical pressure ratio, that's the F sub F, and then multiply it times the vapor pressure. So we'll go to the next slide. We'll show how that. So the F sub F, to figure out what F sub F is, you need to know the vapor pressure of the fluid and the critical pressure of the fluid. And once you know those two things, you put the vapor pressure over the critical pressure, and then you multiply it out with the rest of the formula, and that becomes your F sub F critical pressure ratio factor. For water, so let's take water as an example. We'll go to the next slide. When we work this out, so water, we'll pick 70-degree water. So this is a vapor pressure table, and you can see that the vapor pressure is very dependent on the temperature of the fluid. So the higher the temperature, the higher the vapor pressure. So we'll start with 70-degree water. So we'll take the 0.3631 vapor pressure for water. And then we need to get the critical pressure of water, which we can get because that's a constant, it's not temperature dependent. So you see on the bottom of the column on the right is water, and the critical pressure of water is 3208.2 psia. So we put that into the formula. So we have the vapor pressure 0.3631 over 3208.2. So we square root that fraction, multiply it times 0.8, and then subtract it from 0.96. And the result is an F sub F critical pressure ratio of 0.957.
So really, that's
so
an interesting.
So in this case, I took an upstream pressure of 134.7, a P1 psia, and you'll see that the F sub L squared times this resulting 134.35 is almost the same as your P1. So with water, if you squared the F sub L factor and multiplied it times the upstream pressure, you will basically get your delta P allowable differential pressure, that what is the point that there will be choke flow. So they used to call it allowable delta P.
So that's a really a very good formula, Ralph. If we break it down for water-based fluids, anyway, if you can almost eliminate FF and PV because it's such a small number.
Right.
So
the whole thing is a small number.
Right. So that's small number. So the P1 minus a very small number is basically P1. So if you know your inlet pressure and your recovery factor, you can almost on a napkin in your head figure out if the valve's going to cavitate or not.
So if you're above the pressure or below that pressure.
Yeah.
So if you're pressured. Yep.
So this is very easy for someone to remember. The max delta P a valve can take will be equal or less than the recovery factor squared times the inlet. So, and the recovery factor square is available on everybody's documentation.
So there's other predictors of cavitation as well that other people have developed and have been adapted by ISA. Sigma is another one that doesn't rely on the valve recovery factor that much. It'll give you a good estimation of where you are in your flow regime to whether or not you have cavitation or not. And the sigma is basically the upstream pressure minus the vapor pressure divided by your differential pressure. And then you use the little table below. The number you come up with will give you an idea of what you have for that particular fluid. So either way, I mean, there's all different ways people are addressing cavitation severity. Sigma will give you an idea of how bad your cavitation scenario or regime is in your fluid design stage. There's also another formula. If you limit the trim exit velocity to 100 feet, less than 100 feet per second, you won't have cavitation damage. That's another formula. So there's several formulas that have been adapted to ISA. These are not valve geometry dependent, the sigma or the 100 feet per second. The F sub L way is more tailored to the actual valve and the percent open the valve is, because again, the F sub L factor will change with the percent open the valve is. So you size the valve and you know how far the valve is open, which is what sizing formula in the computer programs do. Then it'll know whether or not you have severe or mild or incipient cavitation.
And I guess we'll discuss that in the third part.
Yep. So the F sub L, all we just went through is just determining what style of valve you pick will be dependent on its valve recovery factor. Now we'll talk about how you pick the right size valve. The right size valve is determined by the C sub V factor. So in order to size a valve, you need to know how much fluid can pass through the valve. So, and then we need to know, when you calculate how much fluid your process needs to pass through the valve, then you need to have a way of determining what the capacity of the valves are you're looking at, and then determine what's the right size valve. So C sub V was developed in the 40s, and it was agreed upon for the whole industry that the C sub V is a unit of measure for flow capacity of a valve. And it's defined as the number of gallons a minute of water at 60 degrees Fahrenheit that will pass through the valve with a pressure drop of 1 psi. So it's just a number that they came up with to use as a standard. So you need to calculate the CV for your particular application, and then match it to, in the old days we used to match it to a table that was published in a sizing catalog that had different CV values for different size valves by percent open, and then determine what the right size valve would be for that application. The rangeability is basically of the valve is basically you divide the minimum controllable CV into the maximum controllable CV for that valve, and you end up with a ratio of how much range you have in controllability in that particular valve trim. So here's the formula for CV, and then there's other formulas, but we'll start with this one. So this is a basic formula. You have your specific gravity, which we'll define in a few minutes, over your differential pressure, square root of that times your volume, how much flow in gallons per minute you're going to pass down the pipe. And then there's a piping geometry factor, which typically comes into effect. The more pressure drop you take, the smaller the CV number becomes. And the smaller the CV number becomes, the smaller the valve size you need becomes, which then you can save money, or and in a lot of cases, controllability, you get better controllability if you put a reduced size valve in the pipe. So if you do put a reduced size valve in the pipe, and it's smaller than line size, that's factor F sub P will make a correction so that you accommodate the line losses from the reducer and expander that you're going to have to put in the pipe in order to put a smaller valve in there. So that's the piping geometry factor, which we'll cover in the next couple of slides. So specific gravity. So specific gravity is one of the key components in determining the liquid, and this is all liquid sizing, but in the liquid sizing, you need to know the specific gravity of the of the fluid, and then it's the density, which is your mass over volume, in relation to a known substance, which we typically use water. So it's basically specific gravity is the density of the fluid over in relation to water. And those are published for most all the fluids that you can get the specific gravity. Again, differential pressure is the upstream pressure minus the downstream pressure. That's your pressure loss through the valve. And then the piping geometry factor is a correction factor based on pipe area reduction to go to the valve, and then expansion when it comes out of the valve if you go back up to the line size pipe. So the piping geometry factor, basically it increases slightly the CV requirement because you are putting an additional restriction before the valve by putting in a pipe reducer. And then the expansion and downstream also puts a back pressure or increases the capability of the valve to send out the fluid at a higher velocity because there's more area. So these factors need to be corrected. But for the most part, it's not that big a deal. It's usually, if you go down one pipe size, you're looking at a correction factor in the 0.92, 0.93. So you're just increasing the CV required in your calculation for sizing the valve about 7 or 8%. It's not a big deal in most sizes. I mean, when you get to a really big pipe, that might be a significant, but it's all relative. So this is from one of the sizing handbooks that H.D. Baumann, Hans Baumann put out. This just gives you an idea of the CV, a quick guide to determine. So you put the CV over the diameter squared for your reducer, and then you end up with the factor below. It saves you having to do a lot of calculations. So if you had the CV over the diameter squared is 10, then your correction to your CV, you divide your gallons a minute by 0.96, and you end up with a slightly higher flow to then use for your CV calculation. Now, viscosity also comes into play when you're sizing as well. Then this is how thick the fluid is, because obviously the thicker the fluid, the slower the velocity of the fluid. Really, this is not that often used because it has to be a very thick fluid, has to be over 40 Steno-Stokes. 90% of the liquid fluids we deal with are below that. So if you're dealing with molasses or heavy bunker oil or asphalt, then that would be an issue that you need to look at. But most sizing programs accommodate that calculation. Like I said, you can do what we're telling you. If you did it by hand, these were the factors you would consider. If you use a sizing program that's already got all these factors included in it, basically you just have to put in the service conditions, and then it'll accommodate all of the corrections for all the different things you need to look at. Now this C sub V value changes with different styles of valves. So the larger valves, obviously, depending on the valve type, can pass a lot more fluid than smaller valves, and rotary valves pass a lot more fluid than globe valves, because the globe valves have that turn through the trim. So here's a comparison. So you got a 4-inch valve. The maximum of full open CV of a globe control valve would be 224. The maximum CV of a segmented ball is 436. V-ball would be 341, and a double offset butterfly valve would be 375. So it's not a significant difference. I mean, it's probably 50% on average, more flow you can get through on a 4-inch double offset valve than a 4-inch globe valve. But as the valve size gets bigger, the rotary valve capacity becomes much more than a globe style valve. And you can see on an 8-inch valve, you've got 3 times the capacity in a double offset valve than you do in a globe valve. And you have significantly more in a segmented ball as well. You get about 50% more. So as the valves get larger, the rotary valve capacities are significantly greater than globe valves, and the cost differential is also greater. So that also goes up. So the bigger the globe valve, the bigger the price difference from a rotary valve.
So Ralph, if you're looking at let's say a 6-inch globe valve sizing application on a 6-inch pipe, you can definitely look at using a 4-inch double offset butterfly valve to be equivalent of the CV curve, right? And also the advantage of a butterfly may be that the rangeability is higher than the globe in the end. A lot of globe valves have 30-to-1 rangeability in the HVAC as an example, and butterfly valves can have up to 50-to-1 rangeability. So you have more range out of a valve that has more flow. And in this case, you can see that if you're using a 6-inch globe versus a 6-inch double offset butterfly valve, the valve would be way oversized and you wouldn't have any control. So many customers I've heard that says that the butterfly valves don't control well is that they changed a 6-inch globe by a 6-inch double offset and expecting the valve to operate at the low end of its capacity, therefore creating the impression that a butterfly valve does not control well. It's just not sized correctly.
Right, that was a point I was going to make. That's an excellent point I always make to customers. If the customers will look at the expense of putting pipe reducers in if they're downsizing one size for a globe valve, but they won't look at using pipe reducers with a butterfly valve, and they need them more with a butterfly valve or a rotary valve than they do with a globe valve. So they try to use line size valves because they're trying to be cheap with the butterfly and rotary valves. So temperature is a critical thing to know when you're sizing control valves, and one of the reasons for that is we went through the cavitation scenario, but that's the reason is the vapor pressure varies with temperature. So if you give us the wrong temperature or you guess at the wrong temperature, you could end up with missing cavitation issues or missing some other issues. And the same thing holds true with some of the other fluid characteristics. The temperature, and this is water, the higher the temperature of the water, the specific gravity changes as well. If you have some other fluids, it may be a more dramatic change than this. If you increase the temperature, the specific gravity will change significantly as well. So the temperature is a critical factor in valve sizing, because you got to know what the fluid is going to do in your pipe, and if you use the wrong temperature, you won't be able to predict what the fluid's going to do inside your pipe. So typically on an on-off valve, you just need to know what the fluid is. Sometimes you don't even have to know what the fluid is, just the line size and the temperature to make sure you got the right trim that'll hold up to that temperature, and the operating pressure range, and what mating flanges or what your end connections need to be, and the material requirements based on the corrosivity of the material going through the pipe. And then your air supply decides the actuator, or your electric current for air supply for a pneumatic actuator, or electric current for an electric actuator. If they want a failed position, shut off, on off, what the shut off pressure is, that's the critical factor. We just size on off valves to shut off the line pressure. And preferred valve style, the customer usually wants a certain kind of valve for an on-off valve and how fast it has to close, things like that. And for a control valve, we need a lot more information. We definitely need a lot more fluid detail. We need to know the fluid name, its properties, and the line size upstream and downstream. We also need to know the pipe schedule because that'll dictate how much flow area there is inside the pipe. We need to know the temperature for the reasons we explained before during each of the conditions that the valve is going to see. We also need to know the upstream pressure and how it varies during different parts of your process, and also the downstream pressure and how it varies different parts of your process. So if you've got 3 service conditions that you think that valve is going to see, if you have 8 service conditions, tell us all 8. The more information that you have to analyze the right valve, the more you're going to get a good operating functioning valve. Again, we talked about this in class 1 for those that weren't there. Control valves are following an ISA ANSI FCI 70-2 leakage rate certification. So these are the maximum allowable leakage at the factory in the manufacturer's test stand when they do the leak test. All of these allow leakage, including class 6, which they consider bubble tight because there's a certain amount of bubbles that are allowed to leak at the factory when the valve is new. Also, class 5 is more for metal seated valves, and that also allows leakage. So this standard allows leakage when the valve is sold to you. It has a leak rate that's acceptable. On rotary valves, which is the next slide, we have a valve that is a block valve and also a control valve. So rotary valves adhere to, if they're soft-seated, which in many cases they are, adheres to the API 598, API 6D soft-seated seat leakage test that's done by the manufacturer at their facility, and the allowable leakage is 0 at the facility. So you have a 0 leakage valve, and that's the acceptance criteria. And it's a lot better if you see the far right column is the FCI 70-2 class 6. They're allowed 6 bubbles of air, 11 bubbles. So there's a lot more allowable leakage in the control valve standards. So in order to get the right control valve, you need to give the control valve manufacturer the function, what the valve does. Is it a daily startup valve? Is it a continuous or an on-off control valve? Is it going to see a long duration at the minimum flow? Because that's usually a critical flow factor for determining how long a valve will last and if it's going to encounter any issues with cavitation or flashing, usually at the min flow. Specify as many service conditions as you can. If you've got 6 different regimes that the valve will see, give us 6 different flow rates. At a minimum, give us 3, max, normal, and minimum. Make sure you give us the right temperature, and then provide the process conditions that will define your performance. Is the valve a control valve for temperature or pressure? We need to know what the valve's doing as well. So what we're going to guarantee is we give you a valve that meets the pressure boundaries. So it's the right ASME class. If you don't specify one, we give you the right one that matches the pressure and temperature. We give you a maximum, hopefully, flow at range that doesn't exceed 80% of travel, and you meet the minimum. We can meet the minimum flow requirement you give us with at least 10% travel, so you have a long service life valve. And we confirm, we tell you we're using what sizing methodology we're using, which most people now are using the ISA formulas, but some people still use it proprietary formulas. So you want to know how to the vendor calculate all these CVs and cavitation potential. And then you get the right actuator that will shut the valve off tight if you require tight shutoff. So next week on Wednesday, we're going to go through actual sizing examples using control valve software sizing, and we'll look at different applications and different ways to pick the right valve to provide good control in your process.
All right, thank you, Ralph. At this point, I know there's been a lot of questions, and I tried my best to answer most of them as we were going along. So last ones I have not answered yet. Let me just read them. Is shut off in class 6 the same? Actually, it is, but at the same time, shut off may be different from one manufacturer to another, or one style of valve in another. Pure control valve, what we call a pure control valve, is a valve that cannot be actuated in any other way than in a control situation. Normally, you classify those as class 1 to 6, like Ralph mentioned, and that's one type of shutoff. And then there's other types of shutoff, like the API 598, that comes from the isolation world, which is zero leakage on elastomer seated valves, or could have some leakage, but much less than class 6 on metal seated valves. So the shutoff is basically what you want. Do you want a valve that doesn't leak at all when it's closed, or do you accept some leakage because the application is tough enough that you need metal seated, therefore there's going to be some leakage that's acceptable, and you may be using a block valve in series with it. You see that a lot in designs where you have a control valve and a couple of block valves on each side, so that the valve could be maintained and removed from the line if it needs to be maintained, and B, you have a valve for shutoff if you really need to completely shut the system down and not lose any flow, or not have any temperature increase or level increase on the weekend because the process is turned off, so you may need zero leakage. Or you buy a valve that does both, and that a lot of manufacturers offer control valves that will be able to do both. There's lots of questions. Let me see some new ones. Are the calculations for steam cavitation choke flow done by using the higher temperature water? Okay, let me just publish that so you can see it. Using the higher temperature water. Well, the calculation is done by using the inlet conditions. So whatever inlet at the control valve conditions are, you take those conditions to do the calculations for cavitation. Obviously, go ahead.
But if you're already steam, then you need to use the gas calculations. This presentation was just dealing with liquid. You don't get cavitation with steam. Steam is already a gas. Right.
If your point was to produce steam out of taking very high pressure condensate and then dropping the pressure into a flash tank or something like that, and then it will become steam, that would require you to do that calculation. But like Ralph says, only if you're in liquid state before the valve. If you're already steam, you're gas. So you've got different formulas for that, which we didn't cover today.
Right, that's turbulent flow. There's what's called turbulent flow formulas for CV, which if you're going to live with cavitation and you're going to live with flashing and you're going through your control valve, then you need to use those formulas for turbulent flow, which you can find in most manufacturers' handbooks. It's a slightly different formula.
Great. Also, there's a question that says, presentation has been very informative. I'd like to get a copy of the slides and an email address. If any of you want a copy of it, the easiest way right now is to provide us your email, and then we will individually send it to you. We're working on an automated system, but it has not reached our desks yet. So in the meantime, we'd love to send it to you. As long as you're not a competitor, we're good with that. And we'll definitely come back to you with the presentation. Rule of thumb for how many sizes smaller than pipe? What's your experience, Ralph, on that? It depends. I guess it depends which style valve we're talking about. But.
Right, but normally the rule of thumb has been two pipe diameters smaller. However, it depends on the size, and there's some people that will go. Okay, there are some people who will reduce even more than that. It's trying to optimize the controllability of the control valve. So what you have essentially is oversized pipe, but the issue becomes a pipe stress issue more than a valve issue. So as long as you make the corrections for the expanders and reducers that are in the pipe, then you can deal with the pipe stresses on that smaller, much smaller diameter valve, then you can go even more. But typically, rule of thumb, 2 pipe sizes.
All right, there's a very good question here, and it is, what are the recommended control travel for each valve type, globe, ball, or butterfly? And I think that's really relevant because a lot of specification usually come to us and say we want 100% controllability, which is not possible. There's no perfect valve out there. So there are always a bottom part and a top part of the control range that's not usable by the application. So typically on a globe valve, you can get closer to the end of the range because the trims are actually cut to fit the characteristics, whether it's linear or equal percentage. We discussed that the first part of the part 1 of this series. And on ball or butterfly, ball, you have kind of an equal percentage curve as well. So you can go further down and up on a ball. So let's say on the globe, you would be, let's say 20/80. On a ball, you may be able to do about the same 20-80% in percentage of the range. And on a butterfly valve, we're probably going more towards the 30-70. And why is that? Because at the bottom, when you're getting close from 30 to 0, the disc is getting really close to the seat and you're creating these high velocities to create the pressure drop only at that edge. And that will create more velocity because it's a high recovery valve. The velocity will be so high, you don't want to start eroding the seat and disc surfaces. So you want to keep the disc away from the seat not to create too much velocity. And on the high end, because the disc of the butterfly valve has a shaft going through it, the trim changes or the volume changes will start to flatten out. So that nice modified equal percentage curve on the butterfly start to flatten out, and it doesn't control, the controller won't see it as well. So I would say 30-70 on a butterfly, 20-80 on a ball or V-ball, and in a globe valve, you can go maybe a little bit more. That's where you would try to stay in that type of range. But it's seldom that we see this type of long or high rangeability requirement, because when we usually ask for the minimum flow controllable and the maximum flow controllable, they usually come right in that range with the selected valve. But it's a very good question. We don't want to work at the bottom of the range. We don't want to work at the high range.
And that's always a question we'll come back with, because sometimes people give us a max flow condition that is not real. So in order to accommodate that max flow condition, we may have to go to a bigger size valve and then move the controllable range up higher where your normal flow is, where you're really going to be controlling. So if we'll ask you if this max condition is real, how often you're going to see it, because we'd rather size it to the conditions you're normally going to run your process at, rather than give you an oversized valve just to accommodate a max flow that may or may not ever happen.
All right, there's another good one here by Mr. Anonymous. If you have a valve right by the inlet of a flash drum, would you consider the K = 1 pipe exit and the FP piping factor? So you're basically connected right against the wall of the flash drum. So it's really not a pipe anymore. It's more like an open vessel. So I think at that point, you don't need to be worried about that factor there.
Yeah, and that's a good design for flashing, because you're not going to do your flash is going into a much bigger area. So the velocities will be controlled immediately as soon as it gets into that much bigger area.
Yeah, so it'll flash really well.
Yes, so that's why they put them against the flash tank.
Yeah, that makes sense, because then if there are carried over water droplets, they'll try to flash immediately and flash away from the pipe or the outlet of the valve. So that's a very good question, and yes, it would be perfect to do it that way. And I think, aside from the question about my birthday, everything else has been answered. So if there are no more questions, we want to thank everybody for their presence today, and thank you, Ralph, for your knowledge and support. And Jocelyn, you did a great job again. Thank you so much. And we hope to see all of you and bring your friends back to the number 3 of this session, which will be how to use a sizing program. This way you don't have to use all of these handheld calculators and formulas that Ralph showed you in theory. The practice is really using a sizing program today to create the ISA sizing sheet with everything that you need to be able to specify and order the right product. So we're going to go through a typical sizings, and it'll be interesting, and I hope your questions will give us some ideas of what to size and put us on the spot. That's always good to try something you've never tried when you're online with everybody, but we'll have fun with it. Just as long as we all understand this is going to be a fun way of how a valve person have to work through to get you the right valve. So we look forward to showing you this next week on the 10th at 10 a.m. Right, Jocelyn?
That's correct.
Okay.
Thank you very much.
Thank you. Have a great weekend.
You too. Bye-bye.